Hello, welcome to this lesson on universal calculator skills. In this lesson, we will cover a whole bunch of different types of things you can do on your calculator that will cover all different areas of maths. Maybe you'll pick up a few little shortcuts or tips or tricks, or maybe you know some yourself that I don't know, but we'll find out. Let's go. So let's look at how you can solve using your CAS calculator. So first we go into a new document. I will always choose to use the numbers instead of clicking on the screen. It's a lot faster. So I click 1 again to add calculator, and now we want to solve this equation that we've been given. So let's use the solve function. We go menu, 3, 1. You'll use solve fairly frequently, and if you can remember those shortcuts and get there in a blink of an eye, that's going to save you a ton of time in your exams. So if you want to put a bit of effort into memorizing these, it'll actually save you a lot of time in the long run. So let's go and solve this equation. So we type it in. When you do your power, make sure to press the right arrow to get out of the power. At the end, after we've typed it in, you will write comma x. That represents that we are solving for x. And once it's entered, we press enter. And those are our solutions. We can see that there's 3 solutions: x equals -4, or x equals 5, or x equals 6. Factorizing and expanding. So we've been asked to factorize this function. We can do that using the factor function of our calculator. So let's go. Menu, 3 for algebra, and then 2 for factor. So similarly to solve, we type in what we want to do the factorizing to. In this case, we just want to factorize the right-hand side of the equation. So we just type in the right-hand side of the equation. And when it's typed in, we press enter. And that's our factorized form of that equation. You can see the dots in between the brackets. The dots represent multiply. When you write this down in your book, you don't need to write the dots in, just the brackets is fine. What we can also do is expand that set of brackets to check and make sure that we get back to the same answer. This also might be just a question that you're asked. It's good to be able to go in the reverse order. So let's also look at how we can expand those brackets. So we go menu, again algebra 3, and this time 3, expand. Now I'll show you a pretty cool trick. You can select something from the screen of your CAS. You can go Control-C, and into the brackets you can then paste Control-V. So just like the shortcut on a computer, some of you might know that, some of you might not, but you can press Control-C to copy and Control-V to paste. That's been pasted in. Now we can press enter and expand those brackets. And there we go. We come up with the original function. That's what we expected, and that's great. We're there. Now let's look at how to solve an equation when you need to have a restricted domain. So we've done just a regular solve over everything, over the whole domain of everything from -infinity to infinity is implied. But we can actually restrict where CAS is looking and where we actually find those solutions. So to tell the calculator to do that, it's very specific. The calculator only understands if you tell it exactly the right way. So let's go through how to explain it to the calculator and tell it exactly what it needs to hear or what it needs to read to give you the answer you want. So we'll use that shortcut again. We'll use that Control-C, Control-V. If it saves us time, we should do it, because in the exam, time is money, and we want to do things quickly and efficiently. So Control-C, then we will Control-V. Great, so it's just the same function as before, so drag that down. Now, to restrict the domain, what we do is we use a vertical line. So to find that, you will look in Control, and then this equals sign. You get these options, and we will choose the vertical line. Next, we type in our restricted domain. So in this case, it's x is less than 0, but you can type in other restricted domains, and I actually encourage you to play around with this. The more you play around with your calculator, the better you get to know it, the better you get to find out maybe there are different ways to do things and maybe you prefer different ways. So don't be shy of getting error messages on this calculator. The more you get error messages, the more you'll learn, because you'll find out something works and eventually doesn't work, and then eventually you'll find out something does work, and it'll be great. So we've got that there. We press enter, and our answer comes out as x equals -4, which is great. So we've found our solution on a restricted domain. All right, let's look at some graphing, general graphing things that are good to know. We're going to sketch this function and have a look at it. So to add a graphing page, the best way to do it is Control plus page, and then by pressing 2, we've added a graph. And if you want to change back between your calculator page and the graphing page, these little tabs at the top, you can immediately just get between the two. You can add as many as you want along the top, but you'll notice that it gets to a certain point and you'll want to start a new document. So here we are, we're in the graphing page. I will type out the function, but you could also do Control copy, but I'll show you just how it looks in here to type it in. So once your function's entered, you press enter, and it's graphed, it's this blue line. Now you can immediately see that that hasn't all fit onto our window, so we need to play around with what our window is looking at and what we can see. So to do that, we go Menu, we go Window/Zoom, press number 4. Okay, we can zoom in, we can zoom out, or we can set the window settings. I'll show you just some zooming in and some zooming out first. This is actually the second option. I would probably prefer you to use the window settings, but I'll just show you what happens when we zoom out and play around with this as well. As I said, the more you play with the calculator, the more familiar you get, the quicker you get, it's all good. So if we zoom out, number 4, center. So this, what you do is click where you want the center of the new window to be. I'm going to pick somewhere up here because that's about where the center of my graph is, as close as I can get. All right, great. We can kind of see the window, but we can kind of see it's messy. So you can see why zooming isn't the best option. I can zoom out again here. Again, it's getting smaller and weirder. I'll zoom out again, just clicking here. All right, this isn't working very nicely. So what I will do now is show you how to manually set this up. This will actually help you get a graph that looks like it makes sense. So we go again back into Window. So we go Menu, Window Zoom, so number 4. And we want to go into Window Settings, number 1. All right, as you can see, these numbers have become really, really strange. So let's delete that and start again. We're going to just choose some numbers. Let's go from -10 to 10. And those will be our x-axis. So our x-axis will go from -10 to 10. And then we do our y-axis, so what we want that graph to go from and up to. So the graph can go from, I'm just going to have a guess here, and I'll show you how you can kind of trial and error and guess these windows. So I'm going to try from -50 up to, let's say, 200. And this is just a guess based on the numbers, based on what I've seen on the graph. And we press OK. And actually, those guesses turned out kind of right. That's just because I've done this a lot. So you'll get better at this the more you do it, just like anything. So you can see the graphs going from 50 up to 200. I would actually probably cut that 200 down a little bit. I think we can, what we can do is make that a little bit less than 200. And the effect will be that the top of the graph here will just move up a little bit more. That's actually pretty minor. I'm very impressed with myself on guessing it like this. But as I said, the more you do it, the more practice you have, the better you'll get at it. So let's have a look how we would zoom in on that x-axis, that y-axis a little bit more. We go Menu, 4, and again 1. So I'm going to change this 200 to, let's see what happens if we make it 160. Press OK. Yeah, that looks nice. That looks like a nicely printed graph. Yeah, so that's how we can edit the window and zoom. First preference is definitely manually changing those windows just by typing in the X and Y. But if you're not sure or you want to just get a feel for it very quickly, you can just zoom in and zoom out. Okay, defining a function. If you've never done this before, this might be your magical key to success. Defining a function, particularly in an exam 2, when it's a multi-stage application task and you're using the same function over and over and over again, defining a function there can save you a load of time. And not only that, if you type it incorrectly the first time, there's no chance for a mistake later. So you're also cutting out the chance of just making an error by typing it in. So defining a function is a really cool trick to know. I'll show you how that works. So what we'll do is we'll jump back into the calculator page that we were on before. And what we do is there's actually a few ways to do this. I'll show you a few options so you can choose, but then use this as much as you can. It's a really great way to stop typing so many things in all the time. So let's go ahead and I'll show you the first way. Method is menu 1, 1, and we can define, let's call it f of x because that's what it's been called in the question. But you might also notice sometimes there's g of x's or h of x. I'd actually keep it consistent with whatever question you're doing. Please note though, if it's a t, it's not going to graph well. It's not going to graph at all because when you're using the graphing function, it's looking for an x. So keep that in mind that if a question has the variable as being t instead of x, you should probably still call it x on your calculator. That's going to be a little bit tricky, but that would be my recommendation. So let's define this. F of x equals, and then I'm going to do the copy-paste trick. Copy, Control C, click down, Control V, and enter. It says done. So let's just check that that's actually done. What we'll do is just type in f of x and see what happens. F of x, enter. And there you go, that function has been defined. I'll also store it in a different letter just to show you how that works in a different way. So we can also do this stow function. So I'll show you how that works by going copy, Control C, and into here, Control V. And then we go Control, the var button. So you're looking for STO with an arrow. That means store. And we're going to store it into, let's call it h of x. H of x, enter, done. Again, we'll check. Let's type it in and see what happens. H of x, enter, and that's worked. So there's two different ways you can define a function, and I recommend that you start using these. Now, I've told you that storing is a great idea and that I recommend you doing it, but let me actually show you the value of it and show you why it is so valuable. So to do this, I will graph using these stored functions. So first of all, I will start a new graphing area. So go Control plus page, so Control doc, which is plus page, add graph number 2, and let us enter f of x and press enter. So what we've just entered is exactly the same as our graph from earlier. The window's a little bit different. So let's change the window so we can see it exactly. Our window before went from -50 to 160. So I'll change that window and we can have a look. Press OK. And now you can see that the graphs on both pages are the same. And you'll also notice that in the way I've just done it, was much quicker to type in because all we typed was f of x and pressed enter. That is the tip of the iceberg of the power of entering and storing functions. Finding the turning points of the graph. This is a really typical, really common question that you'll see in Maths Methods, partially because it actually is a really nice crossover between lots of different areas. So it covers graphing and looking at graphs and kind of investigating those, but then it also starts to cover things like calculus. And you'll notice the recap box over here talks about turning points as being when the derivative's equal to 0. That's not to be covered in this lesson. We're just looking at the calculator stuff. But if that's not familiar to you, please go back and have a look at an earlier lesson on differentiation and turning points there. So what we will do is I'll show you a few different ways to do this. On the calculator screen, we can find the turning points, but we'll find an approximation, a decimal approximation. But then we can jump back into the calculator page and find an exact answer. So how do we find that approximate answer? All right, so let's go. We go Menu, Analyze Graph, number 6, and let's first find that maximum because it's first in the graph, so number 3. Lower bound. What you do here is indicate a point to the left, the lower side of the turning point. So you'll find that and put that in by clicking. Upper bound, so we go the other side of the turning point and click there. And it's told us a decimal approximation for that turning point. This is not an acceptable answer unless the question actually asks for it. So decimals should only be used if the question asks for decimals. Other than that, apart from that, you should always give it in an exact form. So that's fractions or surds or whatever it happens to be. But we're assuming for the time being that it's an approximation. All right, so doing the lower bound here, hopefully you're following along with your CAS and you've kind of already, pieces have connected and you know how to do this lower bound. Just in case you haven't, then that's fine. I'll show you where that is. It's in the same place as the maximum. So we're going to go Menu, Analyze Graph number 6, and then Minimum number 2. So it's the same process again. Lower bound, so to the left, upper bound to the right, and we've got it. That's our decimal approximation for the turning point. Now, how about finding the exact values here? And this is actually the more valuable skill and a little bit harder. We'll need to do that in the calculator screen. And we'll need to remember this theory that's in the recap that the derivative is 0 at the turning point. Okay, so let's jump into here. So what we can do is actually use our solve function again and set it up basically like how it looks in the recap box. So let's have a look. Go Menu, 3 Algebra, 1 Solve. We type in F, we type in Menu, Calculus, Derivative. We are talking about a derivative in terms of x, so the x goes down the bottom. D something dx, so usually we'd write dy dx. In this case, our y is actually f of x that we've defined in our function from earlier when we did our definition. So we'll call that f of x. And I use the arrow to get out of that bracket, equals 0, comma, x. Enter. And those are our exact values for the x values of the turning points. So as you can see, these are ugly looking numbers. These would have been an absolute nightmare to do by hand, but luckily we have technology that can help us out. So this has told us that those x values are these two numbers for those two turning points. What we need to now find are those y values. But again, the power of these stored functions starts to really come into its own here, because what we can do is just say f of these x's. I'll show you what I mean. We can say, calculator, tell me what is f at this point. So what is f at this point? Control C. put it in the bracket, Control V, and enter. And that's our exact value of the y point. Again, an absolute nightmare to do by hand, but we've got it. We've found the exact value. So our first turning point will be x value here, negative root 91 take 7, and that's all in brackets, all over 3. And our y value is this, 182 times the square root of 91 over 27 plus 1,672 over 27. And our second turning point will do the same thing. So we go f, whatever the x value is at that point, so this thing here, Control C, click Control V, and enter. And here we go. Our second value of our turning point is this x value in the brackets, square root of 91 plus 7 over 3. And the y value is 1,672 over 27. Take 182 times square root of 91 over 27. And that's how we can use that stored function to find the exact value of a turning point. Finding endpoints. Again, there's kind of two nice ways to find these endpoints, and I'll show you those two straightforward ways, and you might find your own way, and that's great too. So we're in the calculator screen. I'll go through that way first, and then I'll show you how you can do it in the graph as well. In the calculator screen, what we're trying to do is find the value of those functions at 0 and at 8. So again, we can use the power of a stored function. What is the value of a function? What is the value of the function at 0, at x equals 0? Enter. It's 120. Easy as that. So what about the other endpoint? Well, what is the value of the function at x equals 8? Press enter. 72. So those are our two endpoints. To write this down, you would write them as coordinates, so x then y. So it would be x comma, in brackets, x comma 120, close brackets, and the other answer would be brackets 8 comma 72. Now let's look at how you can do this in the graphing page as well. So I'll jump into one of these graphs that we have. So what is the value of the function at x equals 0? Well, we can do that by going Menu, 5 Trace, 1 Trace, Graph Trace, and we can type in, it's actually already come up here because it happens to be 0. So it says 0, 120. We're actually already done. But if that didn't come up, you can just type 0, enter, and it's there already. Let's do it for the other endpoint so you can actually see when it doesn't just naturally come up. So we go Menu, Trace number 5, Graph Trace number 1. We type in this time 8, press enter, and there's our other point, 872. I suppose the advantage of doing it on the graph page is that it's written in coordinate form already, but both ways of doing it are pretty quick, are pretty sensible. So those are the two options for finding those endpoints.
Hello everyone, and welcome to today's lesson on the calculator skills. If you've found this lesson, you've been looking in the wonderful section of the course called Calculator Skills. We're going to go through the key features and tools of the calculators that can help you to really ace your exams. There are both lessons for the Casio ClassPad and the TIE Inspire, and in this lesson, we're really going to inspire ourselves and go forth. That's the one we're doing. We're going to look at a range of skills, starting off with dividing polynomials, all the way down to using the wonderful define function to work with some composite functions. Let's jump into it. All right, first step is we want to divide polynomials, and that will come up when we are in the land of factorizing. So as a reminder, how do we factorize? Well, you want to find a number first that when you sub it in, you can get 0, so f of x. And let's try f of 1. We get 1 minus 6 minus 9 plus 14. That equals 0. And we have that x minus 1 is a factor. But now you get to this stage where you're like, how do I find the quadratic factor? And there's a range of techniques for doing this, which both Mr. Smith and I have shown in a few lessons. However, you can do it with a calculator straight away. So one technique that people often do is they do long division. You want to divide your cubic by your linear factor to get your quadratic expression. Something goes there. And we can use the calculator to do this. How do we do it? We're going to use the prop fraction tool. The way that we find this proper fraction tool is that we click on Menu, go to Number, and as we're working with fractions, we go to the fraction tools and proper fraction. We press that and prop fraction appears. So you use prop fraction in a calculator, you chuck it in, you put your cubic on the top, you put your linear factor on the bottom, bada bing, bada boom, you have your answer. You know that your function is equal to x minus 1 times x squared minus 5x minus 14. Pretty good. One thing to remember though is you should always check whether you can factorize a quadratic expression. So how do you factorize something? To factorize, you go Menu, Number, Factor. And inside that factor, you can type in the expression you want to factorize. Here's one I prepared earlier. If you factorize your quadratic expression, you see it actually simplifies down to x minus 7 times x plus 2. That's really good. Now, interestingly, you could have actually used your factor expression to factorize your original polynomial from the very beginning. So that would have been the way to, if you wanted to factorize it fully from the beginning. Why did I show you this prop fraction tool? Because you can use it in any case of long division. In this case, because the factorized completely imperfectly, and there was no remainder, therefore factor works, but prop fraction will always work even if you have a remainder as well. So that's what you're going to use for long division. Alrighty, how do we sketch graphs, then analyze them, and find their points of intersection? Well, you go to your calculator, you draw them, and then you use your intersection tool. Let's have a look. You go home. Let's go home. I want to create a new document. I won't save this one, and I'm going to add a graph document. And I want to put in my equations. Now, if we look at our equations, x equals 2y plus 10. That's an x equals. I'm going to have to adjust the format that's been given to me. X equals 2y plus 10. So how do we write x equals 2y plus 10? Well, if you press delete of your equals sign, you get options. And these are all y options. I'm going to press relation because I want a relation between that I can just write straight away where x is on any side of the equation. So x equals 2y plus 10. Boom. And you draw the equation. What about the other one? 4x minus 4y equals 9. Again, it's not in function form. We're going to write it as a relation. 4x minus 4y equals 9. So again, we go tab to bring up a new equation, and it's already in the relation form. 4x minus 4y equals 9. Draw that. Now we can see that we can't actually see our intersection point. So we want to play with the window. Menu, window zoom, and we can change our window settings. I want to see more to the left, so I'm going to make my x min go all the way to negative 20. And I want to see more down, so I'm going to make my y min go all the way down to negative 20. Give yourself room to work with. Draw again, and you can see it appears. Now, how do we find the intersection point? How do you find your intersection point? You press Menu, go to Analyze Graph, Intersection, and here, a little bit to the left, a little bit to the right, make sure the box includes that intersection, and voila, it pops up. You have negative 5.5 and negative 7.75. Now, one thing that's important to note is that the values that are given to you over here are not always going to be exact values. In this case, it is, because there's just 2 decimal places, maximum, and there's nothing that's been cut off, right? But often, you're drawing a graph, and that will be cut off, and it's not actually going to be exact. So the way that you often solve simultaneous equations is by using the equation solver in your main graphs, in your main calculator screen. So you would actually do it here, and you would solve it here to get an exact value. It's important to keep in mind when you're searching for key features of graphs that sometimes you need to go back to your main screen and find the exact values. How do you find the exact values in your calculator screen? Well, that's what I'm going to show you on the next slide. So you want to solve simultaneous equations. You solve the equations of those 2 graphs. Where do you do that? You go to Algebra, number 7, and then number 1, solve systems of equations. You could do number 2 if they're all linear, but number 1 will also work for you every time as well. Once you press solve system of equations, it'll ask you how many equations you want. In here you can say 2, and it'll ask you for your variables. You can say x and y. And then it'll pop out this expression over here, solve. It'll give you your x and y, and all you have to do is put your 2 equations there. If you press enter, you can get your answers as exact values. Now these are the solutions to this equation here. The other thing that we're looking at in this slide is how to tell the number of solutions from your solving. You know, when you're trying to work out the number of solutions, you can have 1 solution. If they're the same line, you can have infinite. Or if they're parallel lines, you can have no solutions. Well, by doing solve on the calculator, that will actually tell you the kind of solutions that you have. If when you press solve, you get a standard just x equals something and y equals something, well, there you have 1 solution. If ever when you press solve, you get this little C1 business going on, y equals C1, and then x is dependent on C1, that's telling you there are actually infinite solutions. Why is that the case? Because y is like a C1, it can take on any values that it wants, right? You just see one that you want, and then you pick it. So you can say y equals 1. And when y equals 1, x equals negative of 5 minus 6 on 3, which is 1/3. And you can also have another value when y equals 2. And you can have another value when y equals 3, or when y equals 2.5, or when y equals negative 1,000,000. And for every y value, you have another x value. So you're actually having infinite solutions. Lastly, if you solve into your calculator and you get the answer of false, that's telling you that there are no solutions, your lines are parallel, and you have no solutions. So that's how you use your calculator to actually tell the number of solutions there are to a system of equations. All right, how do you use the calculator to find an inverse? Well, let's first write it out as y equals 6x minus 1 on 3x plus 2. And we know to find the inverse, you've got to swap x and y. It's important to write down swap x and y to show the examiner that you actually are doing it deliberately. They don't just swap arbitrarily. Once you do that, you have an equation. X equals 6y minus 1 on 3y plus 2. Now, you could solve this algebraically. You could times across, you could expand, move things around, factorize, and get y by itself. Or you could use the calculator. If you go to your solve function and you type in this equation here, x equals your expression on the right-hand side, and you do comma y, solve for y, that will rearrange the equation for you and isolate y. And you actually get an answer over there. You could put that as your answer. If though you were sketching it, you might want to simplify it a little bit further. And here's a case where you could use your proper fraction tool to do a long division, and it'll actually pop out your answer in the hyperbolic form. So y equals negative 5 on 3x minus 2 minus 2/3. And that's a proper fraction involved over here. But this is the really main point of this slide, is that you can use the solve function to rearrange your equation even when it involves two variables. Pretty cool. All right. How do you use your calculator to create matrices and then simplify matrix expressions or even solve matrix equations? Let's have a look. See, on the calculator, you can create matrices using this wonderful button over here. That looks like a matrix. And then you can choose the kind of matrix you want. In this case, we had A being a 2x2 matrix, so you can chuck out a 2x2, and you type in your values 1, 2, 3, 4. And a really cool trick here is to store your matrix under a name so you can call it later. Hello, matrix, how are you? How do we store it? We press Control, and that little stow button is for store with the arrow. So, bang, store. And you can give it a name. Let's call it A. You can do the same thing for B as well. Now that you have both your matrices stored, you can actually call upon these to solve expressions that you want. For example, here we're asking for A minus 2B, and you can do that on the calculator. You can also do A times B as well. Let's have a look. If you just type in A minus 2B, you get the final answer from that expression. And if you do A times B, you get the same thing as well. So once you've stored them with a certain name, you can call upon them as you like. The last thing to show you is how you create matrices of differing sizes that aren't always square or aren't just a 2x1 or a 1x2 matrix. The way that you do this is you go Menu, Matrix and Vector, Create, Matrix, and then you can choose the number of rows and the number of columns that you like. How can you use matrices to solve equations? Well, again, you want to store the matrices that you're working with. So let's go and do that. And we have the matrices stored. Now, how do we actually go and solve this equation? We want to get x by itself. The way that you get x by itself is that you multiply u by its inverse, right? U times its inverse, or the inverse of u times u, is equal to the identity matrix, which is kind of like the number 1 in matrices. The important thing with matrices is that the order of multiplication actually matters. And so it's not like 5 times 3 is the same as 3 times 5. In normal real numbers, the order doesn't matter. But in matrices, it does. So here what we do is we actually multiply by the inverse, but we have to specify where. We're multiplying it on the left. So we times by inverse of u on the left of the equation. How would that look? Multiply it on the left for the left-hand side. Multiply it by the left on the right-hand side. And then the inverse of u times u on the left-hand side cancels out, and you get x equals the inverse of u times w. And we can then go to the calculator and actually find what that expression is. We can represent the inverse of u by doing u to the negative 1 times w, and we get an answer, 9 and negative 5.5. Now, the case where you'd really use this, if you didn't want to do it by hand algebraically and you wanted to use the calculator to support you, is when you're using matrices for transformations. In this case, you have your new variables, equaling a transformation matrix times your old variables plus a translation matrix. And to find what the image of the equation is, so this is the old equation, we want to find the new equation, right? We have to substitute for our old x and our old y, which means we have to get x by itself. The way that you can do that is you can rearrange and use the inverse as well. So move b to the other side, x dash minus b equals tx. And then to get rid of the t, you multiply on the left, because you got to put the next to the t, you multiply on the left by the inverse of t. So multiply by inverse of t on the left. That's the left of both sides of the equation. So we have inverse of t, x dash minus b, equals inverse of t times x. And the inverse of t times t, that cancels out, just like it's like equal to 1. It's equal to the identity matrix. Having fun with t here. I'll drink to that. Now, to find x, all we can see is we just have to put the left-hand side into the calculator and we'll work out what it is. So let's go to the calculator, create those matrices, and then solve it for x. I'm just typed x dash and y dash, and I'm storing it to the matrix z because there's no x dash matrix. But if I press enter, you can see that z is now the name for the x dash y dash matrix. Now that we've stored all the matrices, we can then just type in our equation and find what the answer is. We want to do the inverse of t times x dash, which I called z, minus b. Now, I've done my answer, but you can see I've got a lot of decimals there. I can see quite clearly that's a third, but just to make things clear, I need to make my settings so that I get my answer in exact values. So if I go to doc and my document settings, I can say that I want my calculation mode to be exact. And now it's going to give me exact values. I'll even make that the default. And now I'm going to get exact values when I do my answers. So type my equation again, and bada bing, bada boom, I have my answer in exact values. We've got that our x, which is our old variables, is equal to negative x dash minus 1 on 3 and y dash plus 2. And our old x is x comma y. So we clearly know what x is and we know what y is, and we can substitute that into our equation to find a new one. So y is y dash plus 2 equals root x, so root of negative x dash minus 1 on 3. And then you can rearrange and you drop your dashes and you get y equals the square root of negative x minus 1 on 3 minus 2. That's how you can use matrices and the calculator if you wanted to work with your transformation matrices using the calculator. All right, I've saved the best to last. When you're working with a big analysis question on your second exam and you've got this one function that you're always doing things with, you're subbing numbers into it, you're drawing it, you're manipulating it, you're playing around with it, it's useful to define the function. And I'm going to show you how you can use defining functions in the context of composite functions. So you're given here two functions, s of x and t of x, and you want to play around with them a bit. You want to find what t of s of x is, what s of t of x is. The way that you do it is you use the define. Let me show you where you can find that. You press menu, actions, and define. And in there you type in what you want. S of x equals something. I've done it over here. S of x equals x squared minus 4. Done. It's stored. Now whenever you call upon s of x, it will think x squared minus 4. You can do the same with t of x. And then when you want to find t of s of x, all you have to type in is t bracket s bracket x close bracket, and it will actually substitute the numbers in for you. And you find out that the answer there is root of x squared minus 4. So too with s of t of x, you can type that in and it will produce what the substitution is, and you get x minus 4. So it's pretty cool. Another thing that you could do is you could type in s of t of 2, just a number, and it would spit out the right answer for you. In this case, it would be negative 2. So you can really play around with these functions once you've defined them. Another thing that you can do with these functions is that you can actually sketch them. So if you go to your graphing section and you type in t of s of x, it will actually sketch the graph for you. And I was thinking and saying, can you actually use this to predict whether the composite function exists? Now, it's a bit of an unconventional way of looking at it, but I actually think you can, right? T of s of x, we know that the domain of a composite function is the domain of the inside. So the domain of this is the domain of the inside. It's the domain of s. And if you didn't restrict the function, as in if the composite function existed fully, then the domain should just be, well, what's the domain of s? S is x squared minus 4, that's all real numbers. So if you didn't restrict your function at all, as in if your composite existed, then your domain should be all real numbers. But when you look at the graph that you've sketched, you can clearly see the domain was not all real numbers. It's been restricted from negative infinity to negative 2 and 2 to positive infinity. And therefore what we know is t of s of x didn't actually exist from the beginning, right? If you didn't restrict it, the domain would be all real numbers, but it's not all real numbers. It means you had to restrict it to make it exist, so it does not exist. And what about s of t of x? Well, if you sketch that, we know that the domain of s of t is the domain of t if you didn't have to restrict it at all, right? The domain of t is, well, t is a root graph. It's all positive real numbers, including the number 0. And if the composite existed, then the composite would retain that domain. Well, if we look at the function over here, we can see it is all real numbers, also including 0. We're including 0. And therefore, we did not have to do any restriction. And therefore, the composite does exist without a restriction. So it does exist. Now, this is a bit of a funky way of looking at it. It's a bit unconventional. The standard technique is to think about, the range of the inside and see whether it's inside the domain of the outside. But I just want to show you an example of how you could come towards it by analyzing the graphs. The key idea here, though, is this wonderful defining function. You can use it to create composite functions, and you can even use it to sketch graphs as well, just by typing in those letters, and it produces the function for you. So those are some key calculator skills that you can use for chapters 1, 2, and 3.
Hi there! In this lesson, we will be looking at calculator skills specifically for trigonometry. We will cover a breadth of stuff that you can do in trigonometry. It probably won't be everything that you'll see, but hopefully I'll try and cover as much as I possibly can. So let's have a look. So first up, one of the most important things is to have your calculator set up correctly. There's not too many ways this can go wrong, but the main thing is to make sure that your calculator is in radians mode. Everything in methods is always in radians. So let's have a look at how you do that. Do this with me, and if it is wrong, then we'll fix it now and you will have no problems later. So we're going to go into the settings, number 5, document settings, number 2. And what you want to check here is the angle. So here you can see that the angle is set as degrees. That's incorrect. We want to change that to radians. So here we go, radian, okay, and it's as easy as that. So now that it's in radian mode, we can answer this question. What is 16 degrees in radians? So let's go to a new doc. We will not save doc. Add a calculator. Okay, 16 degrees in radians. So we type in 16 degrees. 16, we find degrees in the pi button. Here you can see the options. The option that we want is this little degree sign. And then we press enter. And you can see that 16 degrees is equivalent to 4 pi over 45. And that value is given in radians. You'll know this from doing the course already or currently doing the course. You don't need to write anything for radians, just 4 pi over 45. And that's how we do it. And that's a good way to check as well. Type in something in degrees and see what happens. Okay, now we've got to find all the solutions to this equation given here. We're going to be able to find infinite solutions because this is a trig function. It's periodic. There's infinite solutions because it just keeps going and keeps repeating forever. Now, to make my life easier, I am going to actually define this function now. I happen to know that a similar equation, the same equation, is coming up later, so this will save time. So we should do it. So let's store this function into a variable, into a letter. We'll call it f of x. So 3 cos 2x pi, which just lives in the little pi button, and I will go control var, which is the STO arrow button. that will store the function into what we want to store it into, which in this case is f of x, and press enter. So now, just to double check and to show you what we've done, f of x, enter, is that function that we typed in. Proofreading your calculator is a really great idea. Please, when you type something like this in, just double check that everything is in the right place. Okay, so let's find all the solutions. To do that, we'll go menu, solve, so 3, 1. We are finding when 0 is equal to that f of x, so 0 equals f of x. You can see why I define the function. It's just going to save me time. I don't have to keep typing it all the time. We are solving it for x. So comma x, we are solving it for x, and press enter. Now you'll see these solutions are not neat and not nice, but what do they mean? So these n1 and n1 here, for every whole number, positive and negative, there is a solution. So you could start with, say, 0. You could substitute in 0 to here and here, and you'd get a solution. Then 1, then 2, then 3, and then you'd need to start going backwards as well, -1, -2, -3, and go in both directions for infinity. And then you would eventually write all of the solutions. But you wouldn't, because you can't get to infinity. But that's what that n means. It means it's a recurring solution. You're probably not going to see things like this. With trigonometry, there's often, well, always going to be restrictions on it if you're asked to solve it. So let's now look at what we do with those restrictions and how we interpret it. So let's have a look at a typical trigonometric equation where we're being asked to find the solutions, but the domain is restricted. So here we're being restricted from negative pi on 3 to 4 pi on 3. The brackets are square, so it's included. So what do? We do a very similar thing to before. I'm going to copy and paste this solve function, Control C, and paste down here, Control V. But this time we're adding the restrictions on. So we do that by going Control the equal sign, and that brings up these options, and we grab the vertical line. Here we can tell the graph, we can tell the solve function what x values we want it to look between, or look from, or look below. So here we need to use the less than or equal to and greater than or equal to signs, because they're square brackets, because they're included, and because that's the language that Kaz speaks. So we write it out by going negative pi. Pi is down here in the pi button, on 3. That value is less than or equal to x. So we find that in the equal sign again. So Control equal sign, less than or equal to x, which is less than or equal to, here, 4 pi, again down here, on 3. So once you've put your domain into that language, into that format, we press enter, and we get our solutions. And we can see that we've got 4 solutions by scrolling across and counting the number of solutions there. So those are the exact answers. They don't look like answers, but they're the exact value answers. We can get decimal approximations for these pretty easily. I'll just do it for the first value to show you how it's done, and if you need to do it for others, then it's just the same. But what we'll do is I'll grab the first x value. So I've just selected that value there, and I'll press enter to bring it down. Then to get the decimal approximation, we just press Control enter, and that's the approximate equal sign. So Control enter, and there we go, it's the decimal approximation here. So approximately negative 1.008 and so on. And that's it. That's how we can find solutions on a restricted domain. Now we want to sketch this function again over the same restricted domain. That's great, that's fine. It's actually super easy because we've defined that f of x. So we'll do what we always do with graphing and add a graphing page on. So we'll go plus page, so Control doc, which is plus page. Number 2, add graphs. And here we don't have to type much, we just need to type whatever we called our stored function. In this case, it's f of x, a nice classic one, but it could be anything, f of x, and press enter. Well, not anything, but like close to anything. Okay, this is currently over the domain -10 to 10. That's not right. That's not what we want it to be. And that's fine. We can easily change that in our menu, window zoom number 4, and then window settings number 1. We want our graph to go from -pi/3 all the way up to 4pi/3. I'll leave the y values. They're not perfect, but they're not terrible, so I'll just press OK and we'll have a look. Okay, and that is our graph. From earlier, we saw that the graph equaling 0 in this domain should have 4 solutions. We can go across the bottom and say there's 1 there, there's 1 there, there's 1 there, there's 1 there. That's correct. There are 4 solutions there, so that makes sense. Depending on the situation when you are graphing this, you may have to label a variety of different things. This does depend on the situation. So this might be a question in a SAC, and your teacher might expect you to go through and label all those intersect points, perhaps labeling all the maximum and minimum points. For this, we're just going to assume that this was perhaps a multiple choice question and we needed to look at the function. But all of those things are skills that we cover in other lessons, and also are something that you can do all of those things on the calculator. Hold on. But all of those skills are things that we have covered in other lessons. So please go have a look if you do want to go through any of those ways of finding different points on the graphs. Okay, let's have a look at one last exam question and how you would use your CAS to go through this. The first part of the question is actually one we would do without the CAS. So I'll just grab out my pen. For the part A, period and amplitude, that's actually fine. That's something we can just read off the equation. Please go back and look at your trigonometry section, your trigonometry videos, or your notebook, or your notes, or your working. This isn't a theory video, we're just going through calculators, but you would just smash this out and write the period and amplitude down. So we've got 406 months. Okay, find the maximum and minimum populations of wombats in this location and find n of 10. That is where you grab your calculator out. Okay, to find the maximum and minimum populations, I would actually be inclined to do this using the calculator screen. If it's not an exact answer, we will need to go back to the calculator. To find the maximum and minimum populations, I would do this using the graph page, but if it's not an exact answer, we might need to go back into the calculator page. It's fine because either way, we're going to set up the and store the function to start with. So to get into a new doc, let's just go back to home and go new document, add a calculator, number 1. Okay, let's store this function. So in the question, they've called it n of t. I'm going to call it n of x and change all the t's to x's. It just makes graphing easier and working within the calculator easier. So we go n, we go 1200 plus 400 cos pi, remember it's x and not t, divided by 3, close bracket. And we're going to store that, so control var, which is sto, store into n of x. N of x. Enter. Okay, done. Now we need to find the minimum and maximum populations. So we'll jump into a graph page, add a graph number 2, and we will graph that function n of x. we can't see anything, and that's fine. We already know that the numbers are going to be quite big, so we need to have a look at a different window. In this case, I probably actually would zoom first, just to get a sense for what's happening. So zoom out number 4. Zoom out a few times. Okay, and we can see that it's all the stuff's happening up here. So from here, I will then look at my question and kind of work out what is going to be some of the limits on this graph. What part should we actually be focusing in on? So we definitely want to zoom in on this information. One thing that we should do first up is we want to cut the graphs at the zeros for 2 reasons. So we know that the time is from a certain time, so there's not going to be a negative time in part of this. Also, you can't have a negative population of wombats. So let's cut the windows, let's cut off the zeros. So x min will be 0 and y min will be 0. Okay. Okay, this is still not looking that great, so we need to zoom in a little bit more on the x-axis. So let's do that. All right, so the x-axis, let's just go, we know that the period is 6 months. So if we look at a few periods, we'll be able to see what's going on. So I think that a number around 40 or 50 would be sensible. Let's just go with 40. And okay. And now it's starting to become a lot clearer. We can see that it's a cos graph now. It's not just a messy thing of numbers. So to find this maximum value, there's a lot of different approaches you can take. Let's have a go at a graphics approach. So we go menu, analyze graph, so number 6, and we want to find a maximum. So all of the maximums should be the same. We click below and we click above, and we can see that the x is 6, but the y is not looking so clear. But the fact that we know that the x is 6 is actually really useful because what we can do is just substitute that in really easily because we've defined our function. So we jump back into the calculator screen and we can just say, what's n of 6? What's the exact value of the y? And it is 1600. So that was what was indicated on here. I just get nervous when it's got a decimal point like that because you don't know if the calculator's rounded or not. But in this case, it turned out to be the exact answer. And we confirmed that over here. So 1600 is the maximum. The minimum, again, we can do it a lot of different ways, but let's try doing this graphically, this graphic way. So analyze graph minimum, a lower and an upper bound. I'm confident that it doesn't matter which max and min I'm choosing because I know about the properties of sine and cos graphs. Here we've been given an exact answer. We've got 9 and 800. Here I'm feeling more confident because there's no decimal places. But if you wanted to be doubly sure, you can go n of 9. Another way of thinking about this is that it's half a period on from the previous answer. So that you could have kind of cut out the middleman and just gone straight to n of 9 or n of 3. 800. Let me just check that I'm not lying to you. So what is n of 3? Enter. So those both give you minimums of 800. So the maximum and minimum populations at this location will be the minimum is 800 and the maximum is 1600. So that's part B answered. And for part C, find n of 10. Again, the magic of storing a function, this becomes a question that takes less than 10 seconds. N of 10, enter. Maybe that took me 3 seconds and we just got a whole mark on the exam. That's really good value for money. So the answer there is 1000. So yeah, it's a few little tips and tricks. I'm definitely happy for you to find your own tips and tricks, but this is a starting point for you to learn from. Hello and welcome to this calculator skills lesson. This lesson will look into exponentials and logs. We'll cover a few different skills to do with calculators and exponentials with logs in this lesson, so please follow along with your calculator. You'll get the most out of it if you're actually doing something while you're watching it rather than just watching me do all the hard work. So grab your calculator and let's get into it. Okay, let's have a look at how you can solve some exponential or log equations on a CAS. This is an exam question from exam 1, notably the non-CAS exam. But you can still use your CAS to find this answer. Maybe if you're doing your homework and you've done this by hand and you want to check it, or maybe this one would come up in a multiple choice question or something like that. So it doesn't hurt to know how to do it. So to do this on the CAS, we just use classic solve function. The thing that's a little bit different about this question is that it's a t. So I can show you how that works with a t, but it's literally just replacing the x's with t's. So we go into algebra and solve and type in the equation. When you're in the power, make sure you press the right hand arrow to get out of the power, equals at the end I'm going to write comma t because we are solving for t in this case, and enter. So there we've got the exact answer. Perhaps it's an application question, perhaps you've been asked specifically to give a decimal answer. In that case, you can go Control squiggly enter, and you can also quickly get the decimal approximation. This is always the second choice, and you only do it if you're asked to do it. The preferred option is just to leave it in that first form, log e of 8 on 3. That is an acceptable answer. That is an exact form answer. Okay, let's have a look at this exam question. Before we jump in, I'd just like to point out kind of where we're jumping in. This is a part 3 of a question. So here, what's been done in the previous sections and also what we've already covered in the previous videos is in the previous sections they've found the endpoints. So in 5AI, the endpoints have been found and the minimum point has already also been found. So we won't perform those calculations here, but there is an earlier video where we go through the steps for finding endpoints and finding minimum points, and all of that applies here. So please go back and look if you are not sure. That said, let's go ahead and work out how we would answer this question in an exam. This is one where we will use our calculators in combination with the answers we found in the previous parts. So we will need to be able to sketch this graph. The graph is called S, and we have been given a domain here from 0 to 5, and that's all inclusive. So we need to show that our graph ends at those points with a closed circle. Okay, so what's the shape of this graph? The quickest, easiest, nicest way to do this is to use our graphics calculators. So if I was actually in the exam actually doing this question, I would have at the start of 5AI, I would have stored this function into a letter, into S here. And I would have called it S of X and called every T an X. But because we're just doing one part in isolation, I will just type it in once and that will be fine. So that's a little bit of that, just so you know. The quickest way to do it when you're just doing one is just type it in. So we're going to graph this function. So 2 e to the power of t on 3, I'm going to call it x on 3. Make sure you press that left arrow to get yourself out of the power. You'll notice as well I used the small negative sign just within the keyboard. It's the safest option when you're doing it within a power or within something like that. Sometimes the calculator gets upset when you do the other minus sign. Sometimes it doesn't. But the more you use it, the more you'll kind of work out its quirks. And if something's not happening, that's a really good troubleshooting thing to try. Try that little negative here in the keypad. Okay, we've typed it in. We'll press enter. I'll create a slider for t. So I've just made a mistake. This has alerted me to that. So I need to go back into my data, my graph entry, and change that t to an x. It's very easy to do. So we'll go back into that. But this is nice for you to see that I make mistakes. So don't feel bad when you make a mistake. Just fix it. So back into that t. So I can just click there and that becomes an x. So that's an easy fix. Enter, no problem, no stress. Great. The lucky thing as well about this question is it's actually already set up what we should have our window looking like. So I'm going to use the graph setup to inform how I set up my window. So setting up the window, we've been through this in previous videos as well, but let's do it now because it's appropriate for this question. Our x min, let's start at 0, and let's go up to, we only need to go up to 5, but yeah, let's go up to 5. That'll be a nice clean way to do it. Whoops. So we need to do that in the x max part, not in the x min. And for the y parts, again, we'll start at 0. Here they've gone all the way up to 10, so let's go up to 10 as well. And we'll be able to see what happens. And okay. Great. We can actually see that this graph just on the right here goes beyond 10 before it goes beyond, so beyond 10 before it goes beyond the 5. So this zoom's actually wrong. I need to go out a little bit more, and I should take it all the way up to the 12 that we can see on the grid. So menu, window zoom. It's pretty quick to change, so it's not a problem. If you see it's not quite right, just fix it and enter. Great, so now I can see all of the graph within this window, and that seems better. That seems like what we want to do. Okay, so now using that graph that we've drawn here, we can translate this onto the graph that we've been presented with. So I'll talk you through that process as we do it. So the first things I'd actually mark on are those points from the previous question that they have asked for. They have asked us clearly to label the endpoints and the minimum point. And the labels have to be in coordinates, not just an x, not just a y, in coordinates in brackets. So in the previous questions, I'm cheating because I already know what they were, is going to be 0 and 10. If you want to practice finding endpoints, please go back to those earlier questions and give it a go. All right, the other endpoint is sitting here. This is a good example of you found an exact answer, which is the correct thing to do. So this endpoint here is an exact value. But on your calculator, it would have been handy, a good idea to actually use that approximately equals button to get a sense for what the number is. But you can see that I've put it somewhere between 10 and 12. And that's what you want to show, that it's somewhere between 10 and 12. Okay, great. So we've got those two marked in. And then we also want to show the minimum point. So the minimum point we have is at 6 and at x equals log E8, just like that. So 6 is the y value and log E8 is the t value. Oh, sorry, the s value and the t value. And the shape we can see on the graph. So make sure you're not going below that 6. The 6 is the minimum point. And the curve looks something like this, but you do have to hit it. So carefully hit it. Don't go beyond it. Don't make it jaggedy. Make it nice and smooth, as smooth as you possibly can. It's actually good. This isn't a, doesn't have to be a straight line. Expect it to be a little bit wonky, but do your best to draw a nice smooth line. And then when you do a question like this, I would encourage you to read over it when you think you're done and just make sure you've included everything they've asked for. So have we sketched the graph? Yes, we have. Labeled the endpoints? Yes. We've got the minimum point? Yes, and they're all written in coordinate form. Perfect. That looks like a fully completed question, and we're done. All right, here's a kind of interesting type of question, and I'll show you how we can use our calculators to help us make something that's very complicated become very easy. So what we have is we have a rule for a graph. It happens to be a log graph, that's why it happens to be in this lesson, but this would apply to any type of graph. So if you've been given a graph, it could be a quadratic, it could be an exponential, it could be a sine cos, that's fine. If we've been given a graph, a function, and we've been given 2 points, so these 2 points here, this technique will work. So what we're going to do is set up 2 equations. We'll use each point to set up 1 equation. So there'll be 1 equation based on this first point, 1 equation based on the second point, and then chuck it into the CAS and solve for these 2 unknowns A and B. So we're doing simultaneous equations. It just doesn't look like that when you first look at the question. Okay, so the first point, the 0 is going to become the x, and the 4 log 7 will become the f of x. So we've got 4 log e 7 equals a log e, 0 plus b is just b. And the second point down here, the f of x value is 0, so chuck that in there, and then a log e, x becomes -6, and then plus b. Interesting here, this has come up just now that 6s and b's, please be careful. I'm sure that fits into another lesson somewhere, but if your b's look like your 6s, it can be a nightmare for you and also for the person marking your exam. So please be careful not to do that. But anyway, we've got enough information now. I'll show you how the CAS can do the rest for us. So we jump into our calculator screen, and this time we're going to do solve, but in a way you've never seen before. So go menu and algebra. And this time we're going to solve systems of equations, number 7. And number 1, solve systems of equations. These are definitely not linear equations. Number of equations we have is 2. The variables we have, let's keep it true to what we're doing and change these. So the variables we have, the unknowns we have are a and b. Great, and then we press OK. Okay, now we've got room to chuck those 2 equations in. So we type in our first equation, 4. Now, please be careful with the ln and the log buttons. ln means log base e, and log means log base 10. So in this case, we want ln, we want log base e. It's just calculated code, so you're just going to need to learn the rules of what it means, and then you'll be fine. So log e7 equals, now within the solve function, the calculator can be kind of moody, kind of fussy. I played around with this one, and the only way to get it to work properly and the calculator to read it properly is to type a times in here. So a times the next thing, which will be log e b. Okay, I press the down arrow to get to the next part. You could also just click into the next part. Please work out what's fastest and do the fastest. Okay, the same in the next line. We need to make sure we type the times button in. Log e -6 plus b, close bracket, and enter. And the answer just spits out. So the answer is going to be a equals 4 and b equals 7. That's not the complete answer. The question's actually asking for the rule for the graph, but we're so close that we can just write it down. So a equals 4 and b equals 7. Therefore, the function will be 4 log base e. Let's look at finding the derivative function using the calculator. And there's your answer. Now, the first thing that I'm going to do is store this function. I know that we are going to use this function a few different times, so in the long run, it's going to save me time by originally at the start storing this function. This time I'm going to use the define function to do that. So we go 1 action, 1 define, and then what we want to do is type in the function f of x equals x cubed plus 2x squared minus x minus 2. And we've been told that that's been done. So to find the derivative, we go to Menu, Calculus number 4, and then Derivative number 1. The first thing we type in is what is this a derivative in terms of. The typical thing will be x. Sometimes you might see a t, sometimes you might see something else. But for now, it's an x, so we type that in. And in this bracket, if you hadn't defined the function, here you would type the right-hand side of that equation and type it all out. Because we have defined the function, here we just type f of x and press enter. And that's the derivative. So the calculator's done that nicely, quickly, and it's actually reduced the errors because as long as we type it in correctly to start with, there's very little chance of making an error. So that's finding a derivative. Hello, welcome to our calculator skills lesson on differentiation. We'll go through a few skills that are related to differentiation. I highly encourage you to go along with me during the lesson, grab out your calculators, type in what I type in. It's how you'll get the most out of this lesson. So now what we want to do is find a derivative at a point. Like many things on the CAS, there are many different ways to do this. I'll show you a couple of different ways. So firstly, one nice way to do it is actually to store this. This time I'll use the store button, the store function, but you could again use the define function. They both do the same thing. I'm just giving you options. I'm going to store it as, let's call it G. It will be important for us to remember that this represents the derivative. So the derivative we're calling G. So to find the derivative at a point, at 2, we just need to look at G at 2. So the answer is 19. And I said I'll show you some different options, so let's have a look. Go into calculus again, and this time we find derivative at a point, number 2. The variable is x. The value is 2. We press OK. And then we type in our function again. So here it's f of x. Enter. So again, we found the answer pretty quickly, pretty painlessly. Yeah, and if you find your own way of doing it that works, then do that as well. But we found the answer. It's 19. We confirmed the answer was 19, and now we can move on. All right, we've done it in the calculator screen, and you've had a go there. So now let's jump into the graphing screen and see what we can find out about the derivative when we've drawn a graph of it, or graph of the function, I mean. So let's add a page. Plus page, add a graph. Okay, again, because we've stored our function, we just saved ourselves a load of time and we can just graph what we've got, f of x, straight away. We want to find the derivative at x equals 2. So we go menu, we want to jump into analyze graph, we want to find the derivative, so we go dy dx, and we've been asked position question mark. You can click directly onto the graph. I want to find it exactly at 2, so I'll type 2 and press enter. And you can see from the graph, this number 19 has popped up next to that point. So that's telling us that at the point x equals 2, the derivative is 19. So that's a third option of how you can find that derivative at that point. Okay, now we want to find the stationary points. We'll start in our calculator screen. So remember what a stationary point means. A stationary point is when the graph is turning around. What that means is that for that one tiny little part, that infinitely small part of the graph where it's turning, the gradient actually goes through 0. And that is what you need to be thinking about when we're going calculus stationary points. So we're finding where the derivative equals 0. Now, there are, again, a number of ways you can use your calculator to find this number. It's best to use the one that makes the most sense for you. I'll show you a couple of options. The first option would be using that g of x from earlier. So we've already defined that our derivative is this thing called g of x. And what we can do is just solve when that equals 0 and find what those x values are. So we do that using the classic solve function, one of your best friends on your CAS calculator. And we're solving for g of x equals 0. So when the derivative equals 0, and we're solving for x. We want to find what x is. Great, so we found that there are two stationary points. There's one at the first x value, there's one at the second x value. These are only the x values of the points, so the next step is to then find what the y value of these are. So it's important to remember and keep a kind of clear head on this. So we're finding the x values when the derivative equals 0, but once we have those x values, to find what the y value is, we need to go back to the original function. So in this case, the original function was what we called f. So we need to find what is the value of f at these points. Again, this is a calculator skills lesson. If you want to go deeper into the theory of that and understand the maths of that, which is really important for this, please go back to those lessons, go back to your notes. This is just about showing you how you can use your CAS to do it. So we've got f. I'm going to grab this whole part and press enter, and then press enter. So that then is our y value at that point, and we can do that again for the second x value. You can immediately see that these are awful looking numbers, but they are numbers. They are exact value answers, but you would not want to be doing these by hand. It's very handy that we have a calculator to do these. So that's the y value of the second point. There are a few different ways to do this, as I said before. Another one would be if you haven't done defined the g of x from earlier, that's fine. You could do solve again. But this time actually just write, we're solving for the derivative of f. So we grab out that derivative function again from calculus. So we go menu for 1, the derivative of x in terms of x for f of x. And we want to make that equal to 0 and then find those x values. So we've got the same answer again. And again, it would just be the same process of grabbing those x values and inserting them into the f. By far the most efficient way to do this is the very first step that I did, set this all up. So remember, please define your function at the start. It makes moving these things around and manipulating them so much easier. So that's how we can do it using our calculator screen. We can also have a go at doing this on our calculator, on our graphing screen, I mean. It's not as easy. My preference is definitely to do it on the calculator page. However, when you do it on the graphing page, you can actually see what's happening a little bit more. So doing it on the graphing page might help you understand what's happening, what the graph looks like, what the graph's doing. But doing it on the calculated page gets you to an answer much more quickly. But you're not going to get to an answer if you don't understand it. So it's actually really good to do both of them and to wrap your head around both of them. So we'll go into the graphing page. We already have our function here. The zoom looks terrible, so what I'll do is zoom in a little bit. So we'll go menu, window settings. I'd like my x's to be a little bit more like, let's go -5 to 5. And for the y values, let's say we'll go from -10 to 10. Okay, enter. That looks much nicer, and we can really see what's going on now. How did I pick those values? I just had a sense for them. I've done this a lot of times. You will, over the course of this year, do this a lot of times. So you'll just get better at guessing what they are. It's actually fine if it takes you 5 goes to get there. Trial and error is what you have to do sometimes. And I don't get it right every time. So we're trying to find stationary points. Let's look at how we can do that. We'll jump into menu and we want to go into analyze graph. So that's number 6. And then we're looking at maximums and minimums. So let's do our maximum first because it comes first. Lower bound, upper bound. So this point here is when the derivative equals 0. It's the turning point, it's the maximum. You can immediately see the problem here when we do it on the graphing page is that we don't get those exact values. We do, however, immediately get approximate answers, which might help you when you have to physically sketch it on a graph. It just depends. You need to read the question closely and see what's required. We can do the same for finding when the derivative equals 0 for that bottom turning point, for that bottom stationary point. Menu, analyze graph number 6, and we want to find a minimum this time. Left side of it, right side of it, and it pops out. So there's a couple of different methods, a couple of different ways to think and to learn about these topics. So please try them all, and the more you do, the more you'll learn. Okay, now we can have a look at how you can use your calculator application to find the tangent to a curve at a specific point. And if you use your CAS wisely, you can actually save yourself a fair bit of working out and even cut out chances for errors. So let me show you how you can do it here. So for this function f of x, we want to find the equation for the tangent given this point. On the calculator, all we actually need is the x value of that point. So in this case, it's going to be x equals to 2. Okay, so in a new document, what we'll do is jump into the function that can actually find us the tangent. So we go menu, for calculus, then to tangent line number 9. So menu for 9. And here what we do is type in the equation to start with. So we have x power of 3, press the right arrow to get out of the index, plus 2x squared again, get out of the index. Okay, now here what we do is we place in the comma and we tell the tangent line what the information is that we have. So in this case, it's that x equals 2. And we press enter. So this here, it looks like a line. It should be a line. It makes sense that it's a line. But if you want to actually double check that this is right, that this is the tangent line, this is a good chance to practice using your graphing function and actually checking this. So let's check that this tangent line, 19x take 26, actually sits on the curve at that x equals 2 value, and that it looks right. So let's go and have a graph. The way I'll do this is copying the function from here. So control copy. I'll add a page, so plus page, add a graph, and paste it into here. Control V. Now I know, because I've looked at this graph earlier, that we're actually going to have to change the window so we can see this tangent line. I'm going to do that now. So the menu, we want to make the window a little bit different. Window settings. I'm going to make my x's go from -1 up to 5. And as I said, the reason I know these values is, well, I have a good guess of them at least, is because I've looked at this graph earlier. So enter. So now we want to put this tangent line in. So again, I'm going to copy that across. Control C and we want to enter into the graph entry function, and now Control V. Enter. And yeah, that looks great. It's sitting tangent to the line. It's touching the line there. It makes sense. You can actually physically see the tangent and the curve. So I would really highly encourage this if you are not sure about your tangent line or you just want to double check, especially if you've got time, if it's during homework time or during class time, actually jump in there and have a look and make sure you can see what's going on and that it all makes sense. So on our graphing application, there's nowhere you can really go and just say, find me the tangent. But earlier we found that the tangent, the derivative, the gradient of the tangent at x equals 2 is 19. So we'll zoom out a bit so that we can see that point, 212. And we can see that it's here. We know the gradient is 19. Now we're in the graphing page, we might as well graph that tangent and have a look at it because we have that power. Menu number 3, graph entry edit, and we'll enter into a function. All right, we'll type in our function, which was y equals, or f2x equals 19 times x, take 26. We can now see what that tangent line is doing. It's touching the graph, it's matching its gradient, and it's going out either side of it. So that's kind of cool. It's a nice way to visualize something that you've probably done theoretically quite a few times. Yeah, so that's something that the CAS is very good at. It's good at showing you things very quickly that are quite hard to draw by hand. Okay, let's have a look at limits. This one, if you're approaching this by hand, the big thing you'd be looking at is the fact that there's an x minus 3 on the bottom. So this is the thing that first you'd have to work out how to factorize the top, how to eliminate that, because obviously you can't divide by 0. It breaks things. So you could do this algebraically and kind of pull it out that way, but let's have a look at how you can use your CAS to shortcut that. So back in the calculator screen, we jump into menu, calculus, number 4, and then number 4 limit. Okay, so the limit that we're looking at here is we're looking at the limit as x approaches 3. And the function that we're looking at is this thing here. So if we were using this multiple times, I would have defined it, but as we're just using it once, it's fine. I'll just type it in. You'll notice I've put in quite a few brackets. Brackets are definitely your friend when you're using the calculator, and press enter. So you can see that the limit as x approaches 3 for this function comes out as 0, and we didn't even have to do any algebra. So that's kind of handy. Okay, we've got a work example here. I'll step you through my thought process as I would approach this. This is off an exam. It's off exam 2. This is the part when your calculator is really going to work for you or work against you if you haven't mastered it, but hopefully you can master it. So what I'd actually do here is perhaps even before the exam, I would have gone into main screen, started a new document, added a calculator, and saved it and called it question 1. Because I know that when I'm walking into the exam, there's definitely going to be a question 1 in this second part of the exam. So that's saved. I'd probably even add a graph page. You might not use it, but this is stuff you don't have to do in the exam if you set your calculator up beforehand. So there, we can just jump straight into question 1. Because it's the start of a big question, the questions in the section 2 of exam 2 are big, you want to definitely define these functions because you can expect to be using them over and over again. So for this one, that's exactly what I'd do. I'd store this function into f of x. So we'd call it 2 cos x over 2 plus pi. Another good reason to save each question separately, so question 1, question 2, and so on, is that you might end up having a few different things that are called f of x, and you don't want to get them jumbled up. So having them in different documents saves that from happening. So we've stored that, and now we want to find the rule for the derivative function. So that's great. We know how to do that. We've done this a few times already. Calculus, derivative. It is in terms of x. That's nice and handy. And the thing that we are finding the derivative of is this f of x. So there we go, f of x. Enter. And that's it. That's right there. This is an interesting one because the way it's popped out in the calculator is a little bit ugly and a little bit not how you would ideally write it. I'd actually make that 5, I'd actually write that 5 out the front, so negative 2 over 5 sine of x on 5. So we'd end up with -2 on 5 sine x on 5. And they've given us a name for the derivative function, so we should use that f dashed x equals. So there you go. It's a quick first mark for your first question. All right, let's have a look at part B. We want to find a tangent line. This tangent line is going to be tangent to the function f of x at the point x equals pi. Please remember that pi is a number, it is a value, so x can equal pi, and we can find the tangent there. So how do we do this? It's similar to before. We want to use that tangent function. So we jump into menu, calculus 4, and then tangent line, number 9. We will use our function. So in this case, I'm going to type it in, but if you have it saved as a function, you can just put that function in, or you could copy and paste it. Whatever's the quickest way, I would encourage you to do it. So cos, okay, here we put in a comma and we tell the tangent line function what we know, and what we know is that x equals pi. So comma x equals pi, and we press enter. And so that has spat out exactly what we needed. We needed to know the tangent line. In this case, it's going to be 2 pi minus x. Depending on the form the question asks for, in this question, there is no form that's requested. But if we needed to write it as, say, mx plus c or some other set of values, just be mindful that the CAS can spit it out in any order. And here the x is actually in the second term. So you might need to do some rejigging if you need to write it in mx plus c form. But yeah, that's a great little quick, nice, neat way to find that tangent line. Okay, here there are a few different things going on. We've been given a graph. We need to find the tangent at a specific point, and then we need to find which of these points actually lie on that graph. So there's a few steps where each step itself isn't too complicated, but there are a lot of places we could make a mistake. So we'll keep that in mind and keep a nice clear head and nice clean working, and let's have a go at how we can do this and how we can take advantage of our CAS for this type of question. So for this, we'll create a new document and add a calculator. So the first things first, let's actually find what that tangent line is at y equals x squared for that point 2, 4. To do that, we go menu, calculus 4, and tangent line number 9. Now we type in the value of the function or the expression. So here it's going to be x squared. And the thing that we know is that at this point it's going to be x equals 2. So we type that in, x equals 2, and press enter. So there we go. Straight away we have the tangent line. It was a nice, quick, efficient way to find that line. Now the next thing we need to do is to find which one of these points actually matches up with that equation. There's a few different approaches that you could take to this. My approach that I'm going to take is actually going through and putting in each of those x values and checking if the right y value is coming out. So for this function, I'm going to change it so that the x is the first x value here, so the 1, equals 0, so that's not right. We were expecting if it was answer A that we would get a -4, so it's not answer A. What about option B? So we can go up and change that 1. Let's see what happens when the x is a 3. It has popped out an 8, so that looks great. That looks like it's the correct answer, but I want to just be 100% sure. Let's filter through the rest of the answers and see what's going on. If you're in exam, probably you would just move on at that point. But because we have time, we might as well double check everything. So what if it's -2? The answer becomes -12, which is not correct. What if this x is a 1? Well, we already checked that earlier. It came out as a 0, so we could also immediately rule out D from this option. The last one is a 4, so let's do that one now. 4, and that's popped out as a 12. So yes, in fact, option B is the correct response there. A nice, quick way to get through a few complicated steps without any option of making a mistake on paper. So yeah, option B is correct.
Hey there. For this lesson, we're going to be working on your calculator skills for probability. This might be a bit bland, so I've brought this habanero chili in to spice things up. We'll be working through the following topics in this video. One of the good things about the Casio calculator is that it has nice prompts and text fields for you to fill in when you're doing all of these. So you very rarely need to type a whole lot of jargon out in a line like you might need to do on the TI Inspire. For all of these binomial problems, we're going to use the main screen. So here for the first one, we want the probability that exactly one apple has a diameter that is greater than 7 centimeters. And we want to go down here to distributions. And we're going to click discrete because the binomial distribution is a discrete distribution. Binomial PDF. And here are those text fields I was talking about. So here we have x, which is the number that we want. In this case, it is 1. There are 3 apples. So here, this num trial is going to be 3. And this here is the probability of success, which is given to us here in the question as 68.75. But of course, that's as a percentage. So we need to divide by 100. So this will be 0.6875. We hit OK. And 0.20 is the probability that exactly one of the apples will have a diameter that is greater than 7 centimeters. Now again, to find the probability that exactly 3 apples have a diameter of greater than 7 centimeters, we're going to go to our binomial distribution under Interactive Distributions Discrete Binomial PDF. This time we want 3 out of 3. So we want XR specific trial to be 3 and our num trial to be 3. The probability is again 0.6875. And here we can see that the probability of getting all 3 of the apples to have a diameter that is greater than 7 centimeters is 0.32. Now the probability that at least 2 apples have a diameter of greater than 7 centimeters is going to be the probability that all of the 3 apples have a diameter of greater than 7 centimeters, plus the probability that 2 of them have a diameter of greater than 7 centimeters. We already have the probability that all 3 apples have a diameter of greater than 7 centimeters, and that's here. So we're going to take this and we're going to add the probability that 2 apples have a diameter of greater than 7 centimeters. So x is 2, num trial is 3, and the probability of success is again 0.6875. We hit OK, and the sums of these two probabilities is 0.67. So here, we're going to learn how to use the binomial CDF function. The question is pretty much the same, except we are now dealing with a selection of 30 apples. So for part A, we need to find the probability that less than 10 apples have a diameter of greater than 7 centimeters. Again, we go to the main, and we're going to go interactive, distribution, discrete, and binomial CDF this time. Less than 10 apples is anywhere between 0 and 9 apples. So our lower is going to be 0, and the upper is going to be 9. The num trial is the number of apples we are selecting, so it's 30. And the probability of success is given as 68.75%, which is 0.6875. We hit OK. And here is the probability that less than 10 apples will have a diameter of greater than 7 centimeters. It's about 1.5 times 10 to the negative 5. Now to find the probability that more than half of the apples have a diameter of greater than 7 centimeters, we again just bring up the binomial CDF, and all we need to do is make sure that we put the right numbers in these prompts. So half of 30 is 15, so more than half is going to be from 16 to 30. The number of trials is, of course, 30 again, and the probability of success has not changed. We hit OK. And here we see that we have a 0.98% chance that more than half of the apples will have a diameter of greater than 7 centimeters. To find combinations and factorials, we're going to need to use the main screen. We're going to bring up the keyboard, And we're going to hit this arrow here and go to Advance. And here we have NCR, which is not the New Californian Republic, but N choose R. So here, this is 5 choose 3. So we're going to go NCR, 5 choose 3, close the parentheses and execute. And we find that there are 10 ways to choose 3 from 5. This 5 choose 3 is again the same. So NCR, 5, 3. And the answer again is 10. It's really good when the calculator actually gives you the same answer for the same operation. If it doesn't do that, get it checked. Now for 10 factorial, we put in the number 10 and we hit the exclamation mark button. 10! There you go. There's 10 factorial. So here we're going to use the main screen to find m. The method for this is the same as solving for a terminal in integration. So we're again going to go to the main screen, and first I'm going to assign this function here, 1/3 of x squared, to a variable. This is because this calculator function here is actually quite ugly, and it's going to be easier if I don't have to type the function out each time. So I have 1 divided by 3 x squared, and I'm going to store that as y, and I hit execute. And that's fine. I want to work in standard form, so I've just changed that here. If I press execute again, it's what I'm after. So we're going to want the integral of y dx evaluated at x equals m. And then we want to take away this same deal except we're evaluating it at 0. And this is going to be equal to 1 because we know that the definite integral between 0 and m of that function is going to be equal to 1. I'm going to highlight all of this. Interactive, advanced, solve for the variable m. Okay. And here we have that m is equal to the cube root of 9. And that's your answer. So here we're going to work with the Casio calculator to find some probabilities from the normal distribution. We're going to go to our main screen for this. And we go interactive distribution continuous because the normal distribution is continuous. And norm CDF. The standard deviation of 1 and the mean of 0 that it automatically gives us means that the standard normal distribution data, which is what we need to be working with from question 1, is already filled in. The lower will be the lower bound, and the upper will be the upper bound, quite intuitively. We're looking for the probability that x is less than 0.25. So the lower bound is going to be negative infinity. And the upper bound is going to be 0.25. We hit OK. And there is our probability that in the standard normal distribution, the value is going to be less than 0.25. Now again for part B. Again, continuous norm CDF. Now we want to find the probability that x is greater than 0.1. Keeping the sigma and standard deviation the same, because we're again working with the standard normal distribution, we fill in 0.1 as our lower bound and infinity as our upper bound and hit OK. And this is our probability that our value falls between 0.1 and infinity. Now to do part C, we want to go to interactive, distribution, continuous, norm CDF again. Our lower bound is going to be negative 0.1, and our upper bound is 0.1. This is given in the question. And again, we can hit OK. And here is our probability that our value will fall between negative 0.1 and 0.1. Now, the next part of this question requires us to do something slightly different. We're going to use a non-standard normal distribution. So again, we go to interactive, distribution, continuous norm CDF. We're told that the standard deviation is 2, so that goes in standard deviation, sigma, and that the mean is 10. Now we fill these out same as before. We want the probability that our value is greater than 9, so 9 will be our lower bound, and our upper bound will be infinity. Okay, and there's the probability that for this normal distribution, our value will lie between 9 and positive infinity. Here I'm going to show you how to use the inverse normal function on your calculator. We go to main, we go to interactive, distribution, inverse distribution, and we go to inverse here. Inverse norm CDF. Now this is where the Casio ClassPad really shines, because we have this tail setting here. We need to find this shaded region here when x is greater than a. So this is the tail on the right, so we select right. If you wanted the bit in the middle, like a symmetric bit, you would go center, or if you wanted the left tail, you would go left. Unfortunately, you can't do that on the TI Inspire, and you have to convert them all. But we have this lucky setting here. We are given the probability, and it is 0.242. We are told that sigma is 10, and the mean is 50. We hit OK, and that's the answer there. The value for A is 56.999. We'll call it 57.
Hello and welcome to Calculator Skills for Statistics. In this lesson, we're going to look at the different features of your CAS calculator that can help you in your study of statistics. Okay, let's start out by looking at how you can use a random number generator on your CAS calculator. This will be a good thing to do if you've been asked to generate random numbers. You really should do it properly and use your CAS. Humans are notoriously bad at actually producing random numbers, and computers are very good at it. So let's jump in and have a look. I'll also let you know that there is a kind of a interesting way that your teacher can set up your CAS or the whole class's CAS so that the way you're generating numbers is always the same as each other or always different to each other. So we'll have a look at both of those things. So let's go for a new document, add a calculator. Okay, so the way we can generate random numbers is we go through menu, 5, then 4, 2, random integer. Okay, we can do this to just find one random integer. So if we go 1, 6, this will give us a random integer between 1 and 6. So this would simulate something like rolling a dice. So we do that, we press enter, and we've rolled a 1. We can actually do multiple rolls all at once. We can do that by typing in here how many we want. So say we want to make 10 rolls of a dice and have random numbers generate those values. We go enter here. There's some stuff that happens in the background of the calculator where you can actually set the random numbers to not be fully random, and I'll show you how that works. So if we go through menu 5, 4 again, but this time we look at seed number 6, what we can do here is set up our calculator and say we want you to produce based on this seed number. And pretty much the seed number has a preset list or a preset way of making the random number generators. So if everyone is using the same seed, you're going to come out with the same numbers every time. So say we want to use random seed 14 and press enter. So we tell our calculator to produce 10 dice rolls, enter. This list will be the same for everyone in your class. If you start your random seed at 14, if everyone starts it at the same time, then they will get the same numbers. So go and experiment with this, compare it to your friend. Let me show you what happens when we change the value of the random seed. So say we go 110, 111, generate some numbers. And if we go back to 14, I'll show you what happens. So we go back to 14, set that into the calculator, and then generate 10 dice rolls. And you'll notice that these values here, so these ones highlighted, are the same as when we first set up the random generator 14. Now, it's not going to be the same 10 next. The way to think about it is each time you set that random seed, it starts from the start of the list again. So we've gone 10 down the list, and then we cut the list and we started in a new random seed. Now here, what we've done is we've done our first 10. We can actually do another 10, and we'd expect them to be different. There's a small percentage chance, and you can work that out if you want, of them being identical. But there, we can see that they are not the same. So we've kind of gone to the second 10 in the list, and so on. So we can, that's one way to make everyone's in a class's random number generators the same. You can also say something like, you and your friend want to produce a different set of random numbers, set your seeds differently, or assign a number to everyone in the class, then the whole class could have a different random seed number. So yeah, if you start to see patterns and similarities between people in the class, it's probably to do with that in the background of the calculator. But there you go. That's a nice handy way to produce a random number. Okay, now we can do something kind of cool with the CAS. We can do simulations of sampling using random binomial situations. So in this situation, what are we looking at? For example, what if we have 100 clothes pegs, or in this case, Jeff has 100 clothes pegs. 62 of them are white and the rest are green. What we're going to do is use our calculator to simulate 10 goes, 10 sample proportions. And each time that we do that, we're going to use a sample of 30. So each of those 10 times, we're pulling out 30 random pegs from the bag, looking at what it contains and putting them back in the bag, and then doing that again and doing that 100 times. But we don't need to even touch a peg. We can just do it using our calculator. So we'll go into our document and add a calculator. So to do this random sampling, what we want to do is jump into menu. We're working with probability and some random features, and we want to work with binomial, so number 3. Okay, what do we input here? The first number we input is the number in each of the samples we're taking, so that will be 30. The next number we put here is going to be the percentage of successes. So luckily in this case, it was out of 100 pegs, so it's pretty quick to see that, say we call pulling out a white peg a success and pulling out a green peg a failure, then the probability of success is 62%. If the numbers weren't as neat as this, you would actually need to work this out, but luckily we've been handed some nice numbers. So 0.62, and we want to take this sample 10 times, so 10 there. We press enter, and this is the outcome. So out of those 30 pegs that were pulled out, this is how many were white each time. And now to do our sample proportions, we simply go back to all our values here and press enter. And then what we're doing is dividing by the number in the sample. So in this case, we're dividing by 30, and these shoot out our sample proportions. These are obviously exact value answers. And if you want approximate answers as normal, you press Control, enter. And so you could read them across by scrolling across here. But yeah, that's how you can do multiple samples of binomial distributions and find out the sample proportions. So we can use our calculator to work with confidence intervals and predictions to do with those intervals. So for this example that we're looking at, there are 25 students in your class, and let's say that 11 of those students have a dog. Using that data, you will estimate the proportion of students at your whole school who have a dog, and you want to have confidence intervals giving a confidence of 95%. So what do? We jump into the calculator, as usual in these calculator lessons. So this time we'll do something a little bit unusual. We'll actually jump into the spreadsheet. So the spreadsheet icon is down here. Okay, and what we want to do is we want to jump into menu, 4 statistics, 3 confidence intervals, and then number 5. So that's 1 prop Z interval. Okay, so what's the number of successes? In your class, you have 11 successes, 11 people with dogs, out of N, which is 25. We want a confidence level of 0.95. That's already been told, and our first result column will leave as that. So we press OK, and then we can read out our values. When we click on it here, we can see the value printed out in the bottom here in the grey area. So that's saying that 24.5 and some extra bits % of your school will probably have a dog with 95%. So when we click in C lower, we get a number printed down the bottom. this number tells us the proportion of students that we think is the lower bound, the minimum proportion we expect to have a dog out of your whole school. So this is saying that just under 25% of students in your school probably have a dog. And what's the upper bound? What's the maximum that we expect? Well, we click into C upper and we can find that out. So C upper is saying that the proportion we expect, the upper proportion that we expect to have a dog is 0.63458, so on. So those two bounds, the lower and the upper, we have 95% confidence that somewhere between those two proportions, the actual proportion value for students at your school that have a dog. So yeah, that's how you can use your CAS to work out confidence intervals and do that type of calculation. Hello, welcome to this lesson on calculator skills for integration. In this lesson, we're going to go through how you can integrate using your calculator and the different things that you can use the calculator to do. Ah, I'm trapped inside a calculator. Someone, let me out. Let me out. Ah! Just kidding. I'm fine. Okay, now let's get serious and use our CAS calculator to do an integration. So what we'll do here, we'll jump into a new document, add a calculator number 1, and into the menu. Now, things in calculus you'll find in the calculus part of the menu. It all makes sense. So we press 4 into calculus, and that's going to be number 3, integral. You'll notice that often in this subject you'll call the opposite of differentiation anti-differentiation. The other term for it is integration, and that's why you look in integral for this. So just a little bit of background information. Okay, we have no values for the terminals here, so we just jump right into the integral and start typing. So we've got 5x to the power 4. Press the right arrow to get out of the index. All right, now minus 2. And same thing, we're going to get out of that index. Plus 19. Okay, and it's going to be dx. Press enter. Great. Now your CAS has found you one answer, one possible antiderivative of this function. Keep in mind your theory from this calculus section that this is only one possible value. You will also need to write plus c if you are asked for a general solution. But for all of those sort of ins and outs of anti-differentiation, go back to that theory section of the videos. This is how you can do it on your calculator. Okay, now let's have a look at a very similar type of question. I'll just show you what happens when we put in the terminals. So we jump back into exactly the same menu, so the calculus menu and integral again. This time we'll type in the terminals, so 3 and 4. 3 and 4. And type in our function. All right, just be careful here that it's going to be dt, not dx. I also wanted to just show you that this works perfectly fine with not an x. Okay, we press enter, and that's our exact answer. Excellent. Just saved ourselves a lot of work. You can find the not exact answer by pressing Control Enter again. And this is an approximate answer. So there's the 2 different types of answers you can access from doing it this way. Yeah, so that's how you can integrate using a calculator. Okay, let's look at something a little bit different. This time we have been given the answer of the integral. We know the value of the integral is 1/4. What we do not know is one of the terminals. And we can use our CAS calculator to do this. We'll be using 2 functions here. We'll be using the solve function and the integration that we were using in the earlier parts of this lesson. So let's have a look at how we'd actually do this in practice. So from the home screen, let's start a new document. Okay, add a calculator number 1, and we'll go find the solve function. So 3 for algebra and 1 for solve. Okay, now what we do is type in exactly what is being said there, and we ask the calculator to find A. So we do that by going into calculus integral from 0 to A, 2x squared dx. Now make sure you press the right arrow here so you can get out of that dx. I'll show you what happens if you don't press it. If I just type in equals here, the brackets come up. So if that happens to you, that's fine. Just delete that equals and press the right arrow to get out of it, and then you're all good. So equals 1/4, comma, and A. So the solve function wants us to tell it what is being solved. So here we've said comma A. That tells the calculator, please tell me what A is. We press enter, and there's our answer. So A is equal to 3 to the power of a third over 2. As simple as that.